Okay, we have one last concept to cover in regards to stresses on beams, and it specifically has to do with stresses in steel beams. So what we see here is what we've seen before, where we're looking at a rectangular cross-section with a neutral axis going right through its center. Let's change my color to something a little darker. That's maybe a little bit better, that blue. And here we see the stress. So assuming that this beam is loaded in the downward direction and it's deflecting downward, this bottom is going to be in tension, the top is going to be in compression. The maximum stress occurs at the extreme fiber, and there's zero stress occurring at the neutral axis. So what happens is eventually you reach a point, and this says SY, this is from an older version of the book, it should be FY. Eventually you reach the yield stress. And if we think back to what the stress strain curve looks like for steel, initially you have an elastic region. And in this elastic region, if you apply a load and remove it, it goes back to its original shape. However, it reaches a yield point and then plateaus. So this is the amount of stress, which we use as sigma, or we could use F now. We're talking about bending in beams. And down here we see strain. So you generally, when designing a structure, don't want the material to exceed the yield stress, because what happens is you get this massive elongation with little to no additional stress. So the material just starts to give way. It starts to stretch out massively. So this generally is considered the yield stress here is considered the failure stress. However, if we look at the way the stress is distributed throughout the beam, although we may eventually get to the yield stress at the top and bottom extreme fibers, as soon as we go inward to the interior of the beam, those stresses decrease. They decrease, and in fact there's zero stress at the neutral axis. So what happens essentially is, if you design the steel beam to only accept loads up until the point when the outer extreme fiber yields, then you still have all this additional strength left in the interior of the beam that you're not taking advantage of. So if you continue to load the beam beyond that point at which the extreme fiber yields, then more of the interior of the beam begins to yield. So now at this point we have a block of material at both the bottom and the top that has yielded, but yet it still has this material in the interior of the beam that has not yet yielded. So we continue to add load, and then we get this block up here and this block down here that has failed, and this interior part of the beam that has not yet yielded is growing smaller and smaller until eventually we reach this idealized condition where the entirety of the beam, from its exterior extreme fiber all the way down to its neutral axis, all of the material has yielded. This is the point at which the steel beam is considered to have completely failed. This is the plastic moment, MP. And MP is equal to the yield stress multiplied by not the regular section modulus, S sub x. We called it just the section modulus before, but technically it is the elastic section modulus. So we want to know, if we want to know the moment that causes this to occur, this complete plastification of the steel beam, it's the yield stress multiplied by Zx, where Zx is what we call the plastic section modulus. So ZX is a property that we use for steel beam analysis and design. We don't use it for concrete. We don't use it for steel. We don't use it for timber or concrete because those materials do not behave like steel does. But the way steel is uniform, homogeneous, its properties are the same in all directions. It allows it to continue to be stressed and stressed and stressed until it eventually reaches this point of pure plastification. So this is the moment, this plastic moment that is used in design. So let's take a look at an example. Before we get to the actual example, let me point out that you wouldn't want to design a beam so that it actually reaches this pure plastic point. This is definitely failure. At this point, the beam develops what's called a plastic hinge. And if we've got our simply supported beam here, it would essentially develop a point in its midspan that does act like a hinge. So it would just begin to bend like that, real clearly in its middle. And so what we do instead is we want to design beams so that the maximum stress is some proportion or fraction of the stress that would cause this plastic hinge to occur. And so we use a factor of safety. And we say that the moment is equal to, the design moment is going to be equal to the yield stress multiplied by the plastic section modulus divided by a factor of safety of 1.67. So mathematically, what we're doing here is we're dividing by 1.67, which is 5/3. Dividing by 5/3 is the same as multiplying by 3/5, or 0.6. So this is oftentimes written as 0.6 times Fy times Zx. So although this is what would cause failure to occur, we don't want the beam to get to that point. We only want it to get 60% of the way to that point. So this could be thought of as a factor of safety. Technically, this is the factor of safety. 1.67 is our factor of safety. But rather than dividing by 1.67, we multiply by 0.6. So let's look at an example problem. We're going to look at example 1412. This is example 1412, where we have, again, a simply supported beam with a uniformly distributed load on top of it. The uniformly distributed load has a magnitude of 1,300 pounds per feet, and the span length of the beam is 40 feet. And we're told that the beam in question is a W21 by 73. So that means that the depth of the beam is approximately 21 inches. It's nominally 21. We'd have to look up the exact height in some type of a reference, like your appendix. And this is the weight in pounds per foot. So a W21 by 73 weighs 73 pounds for every linear foot. The yield stress of this particular steel is 50 KSI. It's made of A992 steel. That's what wide flange beams are commonly made of. So it has a typical yield stress of 50 KSI. We do want to include the self-weight of the beam in our analysis, and we want to determine if this beam is adequate according to AISC specifications. We want to check for both moment and shear. So this overall weight, so the W plus the self weight, is going to be the 1300 plus 73. So that's a total of 1373 pounds per foot. So we need to know what the moment is. The maximum moment is WL squared over 8. Again, this formula comes from Appendix H. For a simply supported beam with a uniformly distributed load, that's the formula for maximum moment. So it's going to be 1373 pounds per foot times the span length is 40 feet squared, don't forget to square it, divided by 8, and we find that the moment is 274,600 pound-feet. So that's a pretty big number. When dealing with steel, we often use kips to keep the numbers a little bit smaller. So that would be equal to 274.6 kip feet. So that's the moment that's being applied to it. Now we need to figure out how much moment is it allowed to carry. So the allowable moment is going to be 0.6 times the yield stress times the plastic section modulus. So that's going to be 0.6 times 50 KSI times, if we'll have to look up in Appendix A, the plastic section modulus, ZX, for a W21 by 73. And we should find in our appendix that that is equal to 172 inches to the third. It's to the third power. Actually, I can fix that. There we go. To the third power. That equals 5,160. Looking at my units here, I have KSI times inches to the third. So the square inches here will cancel out 2 of these, leaving just 1 inch. So it's kip inches. So we've got a bit of an apples to oranges comparison here. 274.6 kip feet is what's being applied. 5160 kip inches is what it's capable of resisting. So to know if this beam is adequate, we need to get them into the same units. So I can just take the allowable moment here, and that is in 5160 kip inches, and convert it by multiplying for every 1 foot there are 12 inches. So divide that by 12, and that gives us 430 kip feet. So this is what's actually allowed, and this is what is actually applied. So is the beam adequate? Yes, we're allowed to have up to 430 kip feet applied to it, and we're only applying 274.6, so it is okay for moment. Now we still need to check out shear, and the time's just about up on my video, so we'll check shear in the next video.